Thank you, Marco. Thank you all. Sorry I missed the starting presentations. Thank you to the chairmen, to Andrea, to Nicola. And okay, now I can start talking about the topic of my presentation, that is 3D survey of the archaeological evidence. Some reflections about scale, accuracy, and level of detail. So in terms of technologies involved, there is no doubt that the digital revolution has taken archaeological survey to the next level. But are we sure that we are also at the next level in terms of outputs? In my paper, I want broadly retrace the main stages of the workflows related to digital surveying for what has been the operational standard for the last 30 years, and to highlight how the different digital solutions proposed responded to the needs of archaeological surveying. The trend we seem to detect is that of a constant improvement in accuracy and speed of execution, balanced by a progressive loss, in my opinion, of the informational component in the surveys carried out from the second half of the 90s onwards. It means using photogrammetric techniques, first the monoscopic and then the structure from motion one. In the second part of the speech, I will then try to highlight in the different moments related to the survey, data production, data acquisition, data reproduction in a digital environment, how having a dynamic environment such as digital ones, that can be GIS, BIM, AR, VR, instead of the static sheet of the graph paper, offer us great opportunities to semantically enrich our survey and to be able, from this augmented survey, to elaborate analytical cartographies. That means phase plan, of course. So before the introduction of photogrammetric technologies, an archaeological survey required an initial selection of points to be surveyed. The complexity of the stratigraphic context was simplified by taking into account the scale at which the survey would be returned. Needless to say, oversimplification meant that the final survey was anchored to a small number of accurately positioned points, leaving room for a considerable margin of inaccuracy. The main focus was on the XY plan, and the Z was often expressed with a few points to represent changes in elevation, often just the minimum and the maximum elevation. The survey was therefore an operation that required analysis of the stratigraphy of the context to be recorded, with a single stratigraphic unit or several stratigraphic units as the main focus, and what lay around analyzed in terms of stratigraphic relationships. Cover is cover, cut is cut. Depending on the stratigraphic unit to be surveyed and the scale of the final survey, the points to be surveyed were selected, and each point was clearly associated with a single stratigraphic unit, or the location where the stratigraphic relationships between several stratigraphic units was visible. After a careful study of the documentation as a whole, not only the map, but also US data sheets, fine cars, plans, sections, Harris matrix, the final plans were composed as if the various stratigraphic plans were notes to be recovered as needed. In the various plans, if the various plans had not contained the stratigraphic information on what they represented, it would have been impossible to compile the final plans. So the post-excavation survey, the post-excavation map. With monoscopic photogrammetry, we moved on to a technique that allowed the acquisition of a georeferenced base from which to draw from the various units surveyed what lay on the plane identified by the ground control points. Complex geometries no longer had to be simplified in advance, and the accuracy of the survey depended on the number of different planes, each with at least 4 ground control points and a dedicated photogrammetry, into which the scene was decomposed. From the survey of the stratigraphic units, we can say that we have moved on to the survey of areas of interest, of palimpsest, where there is, in fact, a palimpsest of the stratigraphic units. The transition from a total station-based survey of individual points of interest to one based on monoscopic photogrammetry has introduced the raster model into the workflow associated with archaeological survey restitution, without, in my opinion, sufficiently highlighting the pros and the cons. The almost absolute interoperability of CAD files with the vector geometries of GIS and the possibility of assigning values to each of them has made the use of monoscopic photogrammetry rasters as a georeferenced basis for the creation of polygons, lines, points to represent stratigraphic units, material culture elements, ecofacts, sample, finds, practically immediate, but therefore absolutely uncritical. Unlike a total station-based survey, where the number itself of the points surveyed depended by the chosen scale of the final plan, a raster photomosaic allows to experience the entire surveyed context in a digital environment that, being multiscalar, enable different levels of detail of the same features. According to its resolution, a photomosaic thus can show at the same time different aspects of a stratigraphical sequence, from the smallest find and ecofact to the entire plan of the building. The problem with raster is that it is not possible to make single objects from the different features represented. There is no way to anchor qualitative data to spatial entities, as can be easily done with vectors. The accuracy of the positioning of a scatter of pottery fragments, a pile of bones, or a mosaic floor has benefited greatly from such a workflow, but one can trace back, in my opinion, to this exact moment, the separation between surveying as an activity of determining the position of different spatial entities and surveying as also an analytical moment of the stratifications brought to light by the excavation. Photogrammetry was not always accompanied by a sketch map, and it was even rarer for the photomosaic to be immediately processed and printed so that it could be sketched directly, having the documented context in front. On the contrary, the introduction of a photogrammetric survey in a GIS environment should have led, first of all, to the recording of individual contexts. We can call it a context survey, in which the various information on stratigraphic units, structures, finds, elevation, etc., could be recorded, and with which a survey guided by data analysis could be reconstructed. That's what we can call the post-excavation survey, benefiting from the ability of the GIS to manage the graphic component together with all the alphanumeric documentation. In this sense, we can say that the digital survey tends toward an objectivity that the pre-digital survey, almost by its very nature, did not have. Unfortunately, this objectivity has been often confused with the uncritical documentation of the various surfaces of interest, without taking into account the need to make all of those observations in the field that alone make possible the objective drawing of the orthophoto, and without which the restitution of the survey is then not possible. In my opinion, the focus immediately shifted to the cost-benefit ratio. It has the speed with which a given excavation area could be returned back to the excavators on the one hand, and the accuracy of the positioning in plan on the XY plan on a very high number of features, provided that they lay on a plane, of course, identified by at least 4 ground control points on the other. The semanticization of the survey implicit in the simple identification of the points to be surveyed with the total station, and made explicit in a CAD by the name of the layer, which usually each one of you remember corresponded to that of the various stratigraphic units in a pre-photogrammetric survey, is reserved for a later moment, that of vectorization in the GIS environment. And this moment has not always been seen as a moment that necessarily followed the creation of the photomosaic. The survey is done and the photomosaic is just here to prove it. The mistake made by many of us has been to see the photomosaic as such a detailed representation of the surveyed area that is in itself the digital replica, the digital twin, we love to say now, of what was surveyed, and thus not to feel the urgency of freezing the stratigraphic information in a vector drawing, which too many projects have reserved for a post-excavation phase, for the off-season. Of course, vectorization months later, and perhaps with operators other than those who actually excavated the context, is more complicated and problematic. With the transition to the surveying techniques used today, structured from motion photogrammetry, laser scanning, LiDAR sensors on Apple devices, there has been a real three-dimensional acquisition of the surveyed scene, in which the elevation element, the Z, is no longer a mere accessory to the map. The level of detail, the resolution, has then been drastically increased thanks to technological progress. What we now are able to reconstruct in the digital environment is, in all respects, the digital replica, georeferenced and metrically corrected, of the surveyed context, processed through point clouds and meshes, and visualized in GIS through GeoTIFF and DEM. We are now able to replace the XY plane accuracy of the photomosaic from monoscopic photogrammetry with an orthophoto model and DEM that combine the precise positioning of what is represented with a very high resolution 3D rendering. This aspect is, in my opinion, has sometimes further aggravated the problem of the semanticization of the survey. If monoscopic photogrammetry was, well, in fact, suited for the 2D or at most the 2.5D management of GIS systems, the processing of surveys in 3D environments requires the use of digital media that go beyond the shapefiles or geopackages that are usually used to manage excavation documentation. As Delunto and Landesky clearly stated, although the term 3D GIS has been in use since the early 90s, today we are still far from reaching the full potential of 3D GIS. And although there is a wealth of studies engaging a range of aspects of the technology, voxels, dams, boundaries, surface, etc., many further improvements are still possible. To complete the concept, one can recall also Merlot's work. Full development of a 3D GIS for archaeological excavation is a complex task requiring extensive research, in particular as the implementation of 3D GIS structures. An operation has yet not reached the standard of the correspondent 2D approach. The choice is between a digital environment whose analytical capabilities on 2D and 2.5D data are well known since the late 90s, but that cannot at the moment perform the same routines on 3D data, and thus requires to downgrade 3D data into 2.5D geometries, the GIS, of course, or other digital environments that can manage native 3D data, but don't have at the moment, analytical capabilities comparable to GIS ones at geographic scale. We are talking, of course, about BIM, voxel-based environments, etc. I personally work following the first choice, the GIS, but I must confess I can't wait to find someone who eventually will make a road through the wilderness of the world. Seen from the perspective of the survey, an archaeological excavation can be divided into three moments. Data production. Excavation continuously destroys and creates the archaeological record at the same time in the field. Data acquisition and data reproduction. Survey is thus exposing a palimpsest by removing soil according to the understanding of the stratigraphical sequence, describing the identified stratigraphic units according to criteria shared by the scientific communities, and analyzing the stratigraphical relationships between the different stratigraphic units. Then acquiring spatial information about the palimpsest exposed shape, slope of the stratigraphic units. And after it, processing the acquired data in order to obtain a digital replica of the survey context, as stratiformation photogrammetry, laser scanning, Apple devices, LiDAR sensors, creating digital features where the complexity recorded about the context surveyed can be transferred, and then using these elements pertaining the same phase, even if surveyed in different palimpsests, in order to communicate meaningfully archaeological data. To be a useful mean of archaeological research, an archaeological survey must go through all of these. There is a little doubt that in almost every excavation, archaeologists carry out the data creation and data acquisition process quite automatically. But can we be sure that data reproduction is always completed to the last step? It's in the attention to the informative value of the digital twin of our archaeological context that I think most of the problems we face as a community lie. Too often we are driven by the desire for maximum accuracy to the detriment of a carefully observation of our context and the recognition of the various elements that make it up. Without these, the informational value of the final map is compromised. The result is that archaeological projects build terabytes of digital archives with hundreds of highly accurate 3D models of their excavated context, but rarely are the point clouds transformed into digital features that are semantically enhanced with the qualitative data recorded for the context itself. With no information about what is represented, a map is simply mute. The reasons for such a situation are many. The processing of the survey left of the horse season, the lack of communication between surveyors and excavators, the lack of a precise plan for the post-processing phase. The problem is that interrupting the workflow before its full completion can leave a project without the expected results of the survey itself, having the excavation documented through meaningful maps. If we agree that an archaeological survey is not only the reproduction of an exposed stratigraphic context, it has the context survey, but also the creation of maps guided by data analysis, the post-excavation survey, that aggregates all the data from the context survey, then the transformation of point clouds and meshes into digital features that can carry meaningful data becomes the main objective. Given for granted the data production, it's in the data acquisition and the data reproduction phase that some final reflections may be useful. Recent survey methodologies, such as laser scanning, stratiformation photogrammetry, and LiDAR sensor from Apple devices, have the potential to acquire 3D data with varying levels of accuracy, and consequently a different investment in processing time. The higher the accuracy, the slower the processing, of course. Reducing the latter without abandoning the former can be crucial to complete the surveying workflow during excavation. The accuracy we can demand from a survey is in fact not an absolute concept, but must be adapted to the peculiarities of each project and even to different contexts in the same project. In his seminal book, Making Archaeology Happen, Design versus Dogma, Carver says that what we see depends on the measures we take to see it. What we see it, what we seek. We need to define what we need to define varies in the scale from the very big to the very small. Describing the acquisition workflow at Çatalhöyük, Bergen clearly described the use of two different 3D acquisition technologies on different scale. The structure for motion photogrammetry for build in 1989 and the laser scan photogrammetry for the microscale. Let me try a fictional example. There is no significance, no archaeological question that can be answered by acquiring stone and brick materials that have collapsed from an abandoned phase of a site with the sub-millimeter precision of a laser scanner. The LiDAR sensor of an iPad can detect the same element in a shorter time and without requiring lengthy post-processing. But in the same context, the collapsed stone and brick materials is believed to be the result of the destruction of an 18th century building by a cannon shot, and one wants to understand the dynamics of the collapse. The accuracy of LiDAR sensor of the iPad cannot be sufficient. As Campana says in his Mapping the Archaeological Continuum, Filling Empty Mediterranean Landscapes, the questioning, analysis and interpretation of archaeological data are of course heavily dependent on the level of an analytical scale. Once a context is digitally acquired and the survey processed, the issue of the scale and the level of detail can become crucial again. Depending on the digital environment chosen for the reproduction of the investigated context, the procedures for creating the features and completing them with the collected qualitative data may vary, but the choice of the exact level of analytical scale required is always crucial in order to avoid wasting time on unnecessary details or losing important data through oversimplification. Accuracy in the acquisition phase and level of details in the reproduction phase are both aspects that cannot be considered an absolute concept, but that are dependent on the analytical scale, and the choice of the correct analytical scale is, in my opinion, the key to ensure a correct 3D survey to an archaeological project. Sorry, maybe it took me a little bit more of my 20 minutes. Sorry, Marco. Sorry, colleagues. I'm done. Thank you.